Take about 20, 30 seconds. We usually get a fairly healthy audience. We get about maybe 10 additional people on the YouTube stream from the Zoom call. So I'll keep, and there's a chat there too. I will keep an eye on the YouTube chat and we'll share any questions there. People are also welcome to use the chat here in Zoom. If you have any questions, please feel free to do that. You can just type something in. Zoom also has a raise hand feature. You're always welcome to make use of that. I'll keep an eye on that as well. And this is intended to be a discussion, so we will have presentation and a demo, but also a discussion. So any comments, questions, feedback anybody has is certainly welcome. And why don't we give maybe 1 or 2 more minutes, and then we can dive in. I know there's some other people who said they were going to join who haven't yet, so we can just give them 1 minute. Sometimes Zoom is not always super easy to get going, especially if it needs an update. So maybe at 10:04 we'll get going.
Okay.
While we're giving people 1 more minute to dial in, I'll just say thank you for joining. This is the first of the virtual Hyperledger San Francisco meetups of the year. This group had been meeting fairly actively before the pandemic. We were meeting approximately every 2 months in person. Obviously, with the switch away from that and 2 virtual meetups, we've had a little bit of a disruption, but I'm glad that we're having another San Francisco meetup. Hopefully this is the first of several coming up until we are able to meet in person again. Just as a general note, if anybody is interested, if anybody's in the Bay Area and is interested in presenting at a future San Francisco meetup, here, let me put my email in the chat. You're certainly welcome to reach out to me and I'll help organize that. We're always happy to have people in the community make use of meetups to showcase work that they're doing. So please, again, I just dropped my link in the chat. Please do reach out. If you're not in the Bay Area, since we're doing virtual meetups, anybody anywhere can dial in. We do have a worldwide meetup community. If you do want to present, but you're not in the Bay Area, I can connect you to the local meetup group in your area. Here, I'm going to drop that too. If people want to see a map of the meetups, I just dropped that link as well. We use Meetup, so if you go to our Meetup page, you can see we have over 170 meetup groups literally all around the world. So if you are based, wherever you are based, I would encourage you to connect with your local meetup group. And if you do want to ever present anywhere, again, reach out to me and I can connect you to those local organizers, and they and I will be happy to help you present. So with that, I appreciate Xilinx. We've been talking for a while about them presenting at a San Francisco meetup group, so I appreciate the time from the Xilinx team to come and do a presentation and a demo. And then after that, we will have a discussion around performance. I encourage anybody else who has questions, comments, their own information to share to please do that in the conversation. I had invited members of the Performance and Scale Working Group to attend. I know at least one person, Vipin, said he would come. Hopefully he'll have a chance to do that. If he does, I can ask him to kind of share what the Performance and Scale Group has been doing. And I know that there's some interesting work from there. But with that, why don't we start with Xilinx? So here, I will hand it off. If you, looks like we've got the screen set and ready to go. So please take it away, Xilinx team.
Hi, everybody. Good morning. My name is Mohan, and I'm going to be doing most of the presentation today from Xilinx. I see that Ji Yang from my group at Xilinx is here, and Haris Javed is also here, as is my boss, Gordon Brebner. So if you have any questions, we have enough people to answer everything. So with that, let me get started. So I'm going to be talking about some performance improvement studies that we have done on Hyperledger Fabric. And I assume everybody here knows about Hyperledger and Hyperledger Fabric. So I won't say too much about it unless you want me to say a few words. If you raise your hand, David will let me know that. So to start with, we started looking at performance profiling and scalability in general for any kind of blockchain. And I'm going to say a little bit about that, then give you something of a company background, who we are and how did we get to this place here in terms of working on Hyperledger Fabric. And then I'll go over what we actually did to improve the performance of Hyperledger Fabric. And after that, we'll have a short demo showing the performance improvement where we run one of the standard benchmarks that are used for Fabric using Hyperledger Caliper. And so G will be running the demo. And after that, we'll have a discussion of how things work, what we need to do in the future, and so on. So that we'll open it up. So moving on to the next section, unless anybody wants me to talk about Hyperledger itself. Okay. So moving on. So this is a slide based on something that was published a couple of years ago, where we had many different applications of blockchains, and people were looking at transaction rates and how many transactions per second can we do, and how high do we need to go, and so on. So at that time, we did a quick back of the envelope kind of exercise and said, let's pick a sample application, right? So this is where you have an electric meter, which is sending out some data every minute, and this data needs to be logged on a blockchain for some reason, right? And then we start with one supplier and major customers or consumers sending the data, and then we said, maybe you'll have 30,000 transactions per hour at that point. And then if you increase it to all the consumers in that area for that supplier, then maybe we go up to 300,000 transactions per hour. And then we go one level up when we have a grid of suppliers and consumers, say the grid in the local area, such as the Bay Area, for example. Then we might go up much higher. And then if you want to model this for a national grid, then you have a really large number of transactions. And at some point, the software just cannot keep up with this. So even assuming that the software can improve 10 to 100x, and the underlying CPUs improve as well, we would still need additional acceleration to be able to process all these transactions at any single node. So that was the thinking. And this is a fairly artificial example, but let's move on to the next slide, right? And so the idea here is to see, what are the implications of all these? So we have implications on the compute side of it. We have implications on the networking aspects and also on the storage, right? So if you increase the transaction per second rate, right? So obviously we need faster execution of the transactions. We need faster peer-to-peer networking. And we need a lot more storage, faster storage. And then the next thing that we're looking at is maybe we want to reduce the transaction confirmation time, right? So again, in terms of compute, we need to go faster. But in terms of networking, if you want to reduce the confirmation time, maybe we need to reduce the latency of the networking. It's not just faster networks, but lower latency networks. And the same thing for the storage. Maybe the storage needs to be lower latency as well. And then the next dimension that we looked at was, okay, what happens if you increase the data size for each transaction? So that means, in terms of compute, we need more complicated transaction processing. In terms of networking, we need to transfer more data, obviously. So the network bandwidth has to increase. And of course, storage goes up again. And then what happens if we increase the size of the peer-to-peer network itself? So that means the consensus protocols need to have better performance. And in terms of the networking itself, it needs to be faster, and we'll need more blocks to be stored. So many of these are fairly well known to everybody, but we just listed them here for the sake of completeness. And the important point to note here is that we need to make sure that all three, compute, networking, and storage, are integrated, right? Otherwise, it doesn't make sense to improve one without improving the other. Okay, so moving on, a little bit about our company itself and what we have been doing in the past in this area. So Xilinx is a company that's headquartered here in San Jose in the Bay Area. We have regional headquarters in Ireland and Singapore as well. And we are the company that invented what's called the field programmable gate array, which is basically programmable hardware. And we produce chips, which is where we started. And these days we produce accelerator cards that you can buy and plug into your desktop or into your server. And we have development kits, which allow you to design your programmable hardware to run on the chips and on these boards. And then we have acceleration libraries that you can use out of the box with some of these boards so that you don't have to do any hardware design at all. You can just pull in these predefined libraries and off you go, accelerating things like machine learning. And these acceleration cards and services are available on AWS and other cloud providers as well. So if you don't want to use your own personal desktop, you can do it on the cloud. So in terms of customers, right? So we have more than 60,000 customers worldwide. And so these customers range all the way from large companies to people playing with a single card to accelerate something on their desktop. So we have a wide range of customers, and that means essentially anybody can use these cards to accelerate anything you want to do. So what exactly does our chip have? So here's an overview of that. So we have shown right in the middle here something called adaptable hardware. So this is something that you can program as software, right? But you can design your own hardware, and then that becomes programmable in this area. And in addition to this, we have standard cores such as ARM Cortex cores for processing, and we have real-time ARM cores here. And then on this side, we have what we call DSP engines or AI engines. So these are more specialized compute structures. And then we have a whole bunch of commonly used features that are hardened, shown down here. So you can see PCIe of different generations and CXL and so on. So these are standard ways to connect your chip to a host computer. And then you have memory controllers. And then you have networking, right, over here. So you can do multiple 100 gig Ethernet streams. You can also do slower Ethernet if you want. And you can do faster Ethernet if you want. And then we have some crypto engines built in, and these are used for inline acceleration, such as MACsec and IPsec. So this is in the networking area. And we have a lot of other features as well. So now this is a chip, and then the chip is sold directly if you want that, and you want to build your own card, or you want to build it into your motherboard, or you can buy it in the form of a card here. So this is similar to a graphics card that you can buy in the market. You can just buy this and plug it into your machine. And it comes with its own libraries that you can download and run on that. Or you can design your own hardware for this part of it and program this card with your own hardware, and you can do your own secret sauce algorithms in here. And you'll notice that this card has 200 gig Ethernet ports over here, and it has a PCIe connector over here. So you can get data streamed in over the network, process it, and send it out directly from the card. Or you can send it over this to the host computer. And the card has a lot of memory as well. So you can store a lot of information on the card itself. And so here's some of the previous work from our group. When we started working on this, many of our customers were already using FPGAs for mining of Bitcoin. And this was before the ASIC miners got into the business. And at that point, of course, everybody started using ASICs. But then, interestingly, one of the major ASIC miners wanted to improve the network performance for their mining proxy. And so we worked with this company called Bitmain. And you can see, this is their card, which has a lot of the mining ASICs. And then you have a Xilinx processor, which is the controller for all those ASICs. And we accelerate the mining proxy running on this thing, this Zinc. Zinc is one of the Xilinx products, one of the Xilinx chips. So this was a few years ago, and then if you want to see the details, you can look it up. This was at the Crypto Valley conference in 2019, which is when we presented it, but the work was done earlier. And then after this, we moved on to looking at Hyperledger Fabric. And we looked at some of the papers that had been published in this area from IBM, from Waterloo, and from others. And we did our own profiling, and we came up with some ideas for improving the performance that we published at a different conference where some of the previous Hyperledger papers had been published. And this was well received, and it turns out that many of the features that we were suggesting had already been implemented in the next version of Hyperledger at that point, right? So we were working with 1.1, and then 1.4 already had those features. So then we said, okay, what's the next thing to do, right? So we took 1.4 and we added what we call the blockchain machine, which is a hardware accelerated version of that. So I'm going to talk a little bit about that now. So what did we do? So in terms of the performance benchmarking, we said the validation phase of Hyperledger Fabric is one of the main bottlenecks. So this is what we found. This is what many others said. And we have a reference to some of these papers below. So the first one is from IBM. The second one is from Waterloo. The third one is our paper, and so on. And so we said, you know, on the networking side, unmarshalling and marshalling protocol buffers is slow. State database access is slow, so we need to cache that. And verification of ECDSA signatures is slow, so we need crypto cores to do that. And so we moved, our solution was to move all that to hardware. And what we do is the block and transaction data is retrieved directly from the network interface, and we process it right there to do the validation in the hardware. So we reduce both the latency and increase the performance. So this is an overview of our concept. So this picture that you see on top here, you'll recognize as the Hyperledger greenhouse. So there's Hyperledger, and then there's various projects there which are somewhat related, right? And then there's Hyperledger Fabric over here, which is what we are trying to accelerate. And then over here is all the tooling, and we use Hyperledger Caliper as part of our benchmarking. This is the tooling that we use to benchmark Fabric. And Hyperledger itself has all these standard APIs. And what we do is we provide connectors to the standard Hyperledger APIs. And then we use those connectors to talk to our hardware, which is shown in red here. And the hardware itself, we can program the chain code itself, and we can configure the system with different plugins, different numbers of plugins, depending on whether you buy a small card or a large card. And down here is some of the common functionality that we call the blockchain machine shell. And here's the board itself. So this shell is the hardware design, the programmable hardware design that we load onto the board. And over here, we go through a typical sequence of what happens when a transaction is generated by a user, and then it's packed into a block and then confirmed back to the user. So we just highlight in each stage of the transaction, which of the three features, networking, compute, and storage, is most used. And eventually, we focused on this part of it because all the others were not the bottleneck. Right? So we focused on stage 4, which is the validation part of it, the block validation part of it, not a single transaction endorsement, which can be done fairly fast on a fairly low-powered container, but this is to quickly validate a large block of transactions. So what did we do, right? So we built hardware accelerators for Fabric, and this was a hardware software co-design setup in the sense we were running the actual Fabric on some nodes, and then our blockchain machine was one of the nodes in that network. And we were going to improve the transaction throughput and confirmation time and so on. And what exactly does it do? It implements a a validation only peer, meaning at this point, right, just for the demo, it does not do any of the endorsement part of it. And it's on a network attached Xilinx Alveo card that you can buy off the shelf. And when we started our work, as I mentioned earlier, we were working with Fabric 1.4. So specifically, we worked on 1.4.5, and right now we are working on upgrading this to 2.2, which is the latest stable version of Fabric. So the demo that we'll show you is going to run Hyperledger Caliper, right, which sets up the network and runs the small bank benchmark. And the setup is one organization with two standard software peers. One is an endorsing peer and one is a non-endorsing peer, just to just to compare the performance of our hardware against these two. And so if you have an endorsing peer, that means it's doing not only the validation, but also doing additional work as an endorser, so which could slow down the validation part of it. And the non-endorsing peer would do validation only, so it's more of an apples to apples comparison. And our blockchain machine, which we have customized for Fabric, right? So we call it Fabric machine here, is on a standard Alveo-based NIC card, and we plug it into a standard server so that we can get some data from the card through simple read writes on registers from the server and print out the results. And the result, yeah, so we saw that we could get more than 10x improvement in the block processing, block validation performance. So at this point, I'll give you a quick overview of what our demo is going to show you, and then I'll hand off to G, who will run the actual demo, and then we'll get back and talk about it and answer your questions. So what is our setup? So it's run using Hyperledger Caliper. This is a standard tool. Caliper actually sets up the network and adds our blockchain machine to the network. It runs the small bank benchmark, collects all the logs, and summarizes the performance. And so I think I mentioned the structure of the peers and orgs already. And here's some more details, right? So we actually run this on 4 different VMs. One VM has the order and certificate authority. One VM has the non-endorsing peer, and one VM has the endorsing peer. They're both doing validation, and each of them has 8 threads to do the validation part of it. This is the validation system chain code execution. So then we have the blockchain machine peer over here, and this one has 8 transaction validators, 8 crypto cores and hardware. And this is to make this comparable to these 8 threads over here. And then we finally have another VM to act as the client, where you have multiple client processes sending out transactions at different rates that can be controlled. Okay, so with that, I'll now hand off to G, and then we can come back to discuss the results. G?
Hello, let me share my screen. Okay. Oh, hello, everyone. My name is G. I'm working with Mohan at Xilinx. Now let me start the demo. Okay. Yeah. So our script will initialize the fabric network, including service containers, VMs, peer containers for the category.
There is a question in the chat about if it's possible to increase the font size.
Oh, let me check. Okay. Works. Oh, is this gonna be better? Hello?
Yeah, I'm looking to see if the person is responding on chat. They haven't yet. But yes, thank you for making it a little bit bigger.
Yeah, it's a little bigger, but I think, yeah. All right. Okay. Now the system is start. Now I can start our blockchain machine on another server. Okay. Okay, now Hyper benchmark will start. And at the beginning, it will start the channel and initialize the small bank chain code, as well as the users to submit transactions. Yeah, so here is a runtime transaction submitting rate. And this commit error is actually because the Hyper is trying to generate some transaction with MVCC conflict error. So this is normal.
Right. So the benchmark has good transactions and bad transactions, and we are able to flag the bad transactions correctly.
Yeah. Yes. The benchmark is finished. Now it's start to stopping all the nodes, and well, yes. And this script will help us to check the output of the hardware peer and the software peer. Okay, so log check complete. We found there's no mismatch between hardware and software result. So let's come back to the test bench. Okay, it's done. Okay, here we can also generate some report based on the output. These are the statistic results for the software-based peers and hardware-based peers. And now you can see there are. Okay, we can calculate that. So based on the latency, yeah, we actually see like a 15 times speed up here. Here's the result. Okay, Mohan.
Okay.
Okay, let me stop sharing here.
Yeah, thanks, G. So let me share my screen again. Okay. Yeah, so a couple of points here, right? So, you know, as we mentioned earlier, right? So this is for a single peer validating one or more blocks of transactions. And typically the validation phase is followed by a ledger write phase, which can be done asynchronously so that it does not affect performance. I believe this has already been implemented in Hyperledger 2.2. So we do not consider that part of it over here. And so here's the number of transactions per second if you're looking at that kind of metric. And so the standard peer was doing something around 3,000 transactions. And this blockchain machine was doing around 46,000 transactions per second. So the speed up, which you already saw, was 15 point something for this particular run. Yeah, so when we first measured it, it was around 14.5. So that's what we said. So that's roughly, so the goal was to have it to be bigger than 10x. So what's next for us? So we're in the process already of migrating to Hyperledger Fabric 2.2, which is the current long-term support version. And you know, we'd like to profile and accelerate other blockchains as well. And we'll be happy to collaborate with others if they're interested in doing some of this work. So we just listed other projects under the Hyperledger umbrella, such as Quorum, Besu, and Sawtooth. And you know, we're also interested in collaborating with any researchers who are trying to define new blockchains. So if you want to do something which can take advantage of hardware acceleration, but at the same time, you know, the hardware acceleration is not limited to a few people who can build ASICs, but it's widely available. So anybody can go out and buy one of these cards for about the same price as a GPU accelerator card, and you can put that in your desktop. So, you know, anybody who's interested in building up new blockchains or defining new blockchain algorithms based on some programmable hardware like this, yeah, we'll be happy to work with you as well. So with that, yeah, we can start taking questions.
Thank you so much for that presentation and the demo. I guess I can start with one question. You had talked about collaboration, and that's great that you're interested in collaborating with the community on this. And maybe I just missed it, but is there, how would somebody get in touch with you? Is there maybe a a good place to have a discussion or an email, or if somebody did want to, like a researcher, for example, to your point, wanted to connect, is there, maybe you could drop that in chat if there's a great place to get in
point.
touch.
Yeah, so yeah, you should feel free to email any of us. Okay, so we should put our email address on the chat. So sorry, missed that. And I should also mention that, yeah, we are in the process of putting some of this code in open source so people can take a look at it. So the plan is to initially put our code on GitHub on our own area, and then migrate this to the Hyperledger area as Hyperledger Labs project. So that's coming soon. We're not there yet. But at this point, if you want to collaborate, you can always send us email.
That's great. Yeah, thank you for adding your email. And to your point, when you do have the labs project ready, we can do another meetup so people are aware of it. I also did drop a link. In addition to reaching out to you directly, the Hyperledger community does have a performance and scale working group, which has a public mailing list. That could also be a good place to have that discussion. And with that, Vipin, I don't know, Vipin Brathan, do you want to say a minute or two about what that performance and scale working group is, and just if people are interested in collaborating, and if that's on performance issues, if how they could make use of that as a place to do that collaboration?
Indeed, I'm here as Mark's emissary, and we had the same presentation, or similar presentation, at the Performance and Scale Working Group. In fact, the video is available, I believe, or at least the slides are available. Performance and Scale Working Group has mainly been working on, making these presentations available from various people, including the Waterloo guys, and there was, of course, you, and there were people who did client-side grouping. So because that is a completely different approach, maybe that can be combined with this approach and even the Waterloo approach, because that is a yet another attack on the endorsers, where the endorsement peers are separated out. And indeed, even the Oracle blockchain stuff that uses different database, in-memory database, I believe it's Berkeley DB, to do the acceleration. So if you combine multiple methods that are orthogonal, then it's possible that we can get even more speed up. And the Performance and Scale Working Group would be a good place to bring all these streams together. But of course, the Xilinx project itself is very exciting, because I saw that presentation and now this, and it seems like you guys have done some significant speed up. So in terms of actually doing stuff, we can have it housed inside Hyperledger Labs, which is another place which is an open source repository, or a place where people can come together in the beginning to do these kind of experiments. But obviously this needs more than just open source code. You need the actual hardware accelerator, or at least access to something in AWS for doing this. I do have a couple of questions, but I think I'm going to wait because I don't want to take up all the time. Just want to wait for others to ask questions, and then also make some suggestions about where else this kind of acceleration would be useful for the general blockchain space.
Well, Vipin, that's great. Thank you for the update and kind of the context for the performance and scale group. And yeah, we'll definitely get to your questions, but thank you for giving the space to others to ask questions first. So if anybody does have a question, there are a few different ways to do that. You can raise your hand. You can use Zoom to raise your hand. You could type something out in the chat, or you can just unmute yourself and ask. Are there any questions about the Xilinx demo and presentation, or about performance in general that anybody has? I see Nima, you had raised your hand.
Yeah, so hello, Juan. This
Hello.
is Nima from Trinity College. I'm a researcher, and I'm also a member of the Telecom Special Interest Group of Hyperledger. So regarding our own experiments with Hyperledger Fabric, so what we often face is the problem with the inter-machine latency, which is like the network latency.
Right.
That is quite troublesome, and that's kind of plays the biggest role in our latencies and kind of taking down also the transaction throughput. So what I understood is that so the plan of Xilinx is to have these kind of FPGAs ready, or like the boards ready to kind of act as like Bitcoin miners, but for Hyperledger. So you'll have like peers running like a big peer, like imagine a bigger network, right, with much higher transaction throughputs. And is this going to be, say, if you have 5 organizations, 2 peers each, is this going to be 10 Xilinx kind of boards? And then like how is it going to play out with the inter kind of board latencies and so on? And then like where do you see the trade-off there?
Right. So in terms of the latency, right? So one thing we cannot do anything about is the time it actually takes for a packet to go from go across the network, right? But what we can do is, as soon as the packet arrives at our card, we can process it right away. So we save quite a bit of latency there in terms of the time it takes for the standard networking stack to get all the packets in and then assemble them and send them up to the host and copy them multiple times from the kernel memory, the Linux kernel memory, right, to the user space memory where the application can deal with the data. So we can definitely save a lot in that latency, right? Because we can process everything in the hardware as soon as the packet comes in. We can set up filters so that all the other packets can go to the host, but the packets of interest can be processed right in hardware. So that's something we can do. And some other things that we can do at this point are, because we are able to play with the standard networks that people define. So you know, if you are an organization that wants to try acceleration for some reason, right, and you can get your card and put it in there in one of your peers. And if you're an organization that doesn't care about this, then you can continue to use the standard software peers. So you can mix and match software and hardware peers. So that's a possibility also. And you know, one way of doing this might be you have number of you know, small containers for doing just endorsements, and then you have a blockchain machine connected hardware peer, right, to do the validation part of it. And you could have, you know, one in each org, or you can have multiple of these in each org, depending on the size of your network. Right? It's completely scalable.
Great, thank you for that question, Nima. In terms of other questions, I will point out that I believe Hyperledger Caliper as a tool was mentioned in the presentation. I do believe we have some people from the Caliper community on the call. So if anybody has Caliper questions in addition to questions on Xilinx, feel free to ask. And I do see that here, and I will drop a link to Caliper project in the chat, by the way. And I do see that Daniel in chat just asked a question. Daniel, do you want to unmute and ask your question, or if not, I can read it?
It's fine, I can unmute it. Can you hear me?
Yes.
Yes.
Okay, so thanks for the talk. Let me also enable this. Okay. So my name is Daniel, and I'm a researcher in Portugal, and actually started working with consensus and distributed systems and got interested in Hyperledger Fabric recently. And I'm playing around with accelerators as well, and with Caliper. And one thing that I found that is quite tricky is how do we find the proper parameters to compare? I mean, I found out that setting up the Fabric network parameters with Caliper has a huge impact in the results. So it's kind of hard to decide, especially when we have nothing to compare or no guidelines on setting what are the parameters that we should use to perform a fair comparison. So what you're experiencing, what it is your experience in setting up these parameters, and what would you recommend for the newcomers?
Okay, so I'll try to answer part of your question, and then if my friend Harris is still online, I'll see if he can provide some more answers. So basically, we took Caliper out of the box and used the standard parameters, but then we also wanted to get more fine-grained measurements. So we actually added some instrumentation to Caliper. We added some code to it, essentially, to print out more results and data. And then we had our own scripts to collect all this together. So I don't know if that fully answers your question. And if Harris is around, maybe he can chime in.
Yes, and thanks, Mohan.
Thanks, Harris.
No worries. So I just looked at your questions in the chat. So I'll go through those first quickly. They're very good questions. The test environment and the parameters really matter a lot. So it's not easy to kind of compare the results from one paper to another paper because you change the parameters slightly and the results could be very different. But in general, if you are using a bigger block size, you would see better throughput, but at the cost of higher latency for the block as well. So it really depends on the real application, that what kind of a block size makes sense in terms of the trade-off between the throughput and the latency of transactions being committed to the ledger or the state database. So that's just a general comment about the block size. In terms of the VMs, we were running all the VMs in the same server. We have done experiments with VMs running in different servers as well. That does have an impact on the performance. So if let's say I have a server with underlying 32 cores and I could create 2 VMs, 16 core each, then that's still fine. But if you go beyond 2 VMs, then you would see some hit on the throughput gained by the peers running in those VMs. I typically always prefer to have the VMs in separate servers, so that there is so that the measurements we are doing are much more representative of what actually is happening if I was able to run these in standalone servers. In terms of what parameters did you choose for the Fabric network? That's a very general question. Would you like to elaborate what kind of parameters you're talking about? In terms of the block timeouts, we used the 1 second timeout. And in terms of the block size, we used 100 transaction block size. And is there any other parameter you would like me to talk about?
The size in megabytes of the block itself.
I think that was set to the standard value in Caliper, which is probably 100 megabytes or 99 megabytes. So in our case, of course, the transaction rate is a bit higher, so the blocks would be created as soon as you would get 100 transactions. So I'm sending transactions at an aggregate rate of 500 transactions per second, and the block time is 1 second. So the blocks would be more or less 100 transactions each.
Okay, thanks a lot.
Great, thanks for that question. And I see on chat, one of the Caliper maintainers had just pointed out that they're here to answer questions. I don't know, Attila, since we're talking about Caliper, do you want to just give everybody a very brief overview about what it is and maybe where to find out more and how to get involved? And then if people have specific questions, they can ask.
Yeah, sure. Hi, everyone. So Caliper is basically a framework for distributed load generation, and it has a pretty good integration with Fabric. A few of Fabric SDK, previous SDK maintainers are also now maintainers of Caliper. So I urge the Xilinx guys to also check out the newer versions of Caliper, since now we support truly distributed load generations. So you can go way above single host limitation. And it provides nice integration with usual infrastructure supports like Prometheus and stuff. So if you want to ramp up your workload, then definitely consult us and try the new versions. Great,
thank you for that. Are there other questions? I realize that we're at the top of close to the top of the hour, although we did, and some people may need to drop off, but we did schedule for an hour and a half. So there is time for more questions. Please do feel free, if you have questions, to raise your hand or put something in chat or just unmute. Any questions, additional questions?
David,
Is there any? Yes, go ahead, Vipin.
I had a few, but I just wanted to make sure that we give space to everybody else.
Well, I appreciate that, but it sounds like maybe there aren't other questions right now. Yeah, please go ahead.
So a couple of things. One is, when we run these performance tests, it's often with sort of dummy transactions. The performance and scale working group had started modeling a use case so that using that use case, we could generate near real transactions and then use that, not only the transactions themselves, but model the sort of a flow, meaning the rates, sorry. That means you would have natural ebbs and tides in the transactions submitted to the blockchain. So instead of just going all out, so there would be some kind of simulation. So that is an interesting approach, but we really did not have time to do that. So it would be great if we get back into that. I started defining a supply chain use case with several actors, and we were going to get more data from others who had implemented stuff. So this is the only way we can really compare different blockchains, for example. Not just the same blockchain getting speeded up, but often people want to compare different ones. But of course, in your case, since you have instrumented your solution to fit Hyperledger Fabric, it would be difficult. But you did mention something else, which is that you're interested in other blockchains. So I'm wondering about your efforts there, since, I'll tell you why I'm asking this question, but before that, you should probably talk about what it would take to extend, to other blockchains.
Okay, so in terms of extending this to other blockchains, so at this point, we do not have too much experience with every blockchain there is, obviously, right?
Well,
And so it would help to work with somebody who knows that blockchain well. And then if they know what the bottleneck is, and then we can work with them to see how we can accelerate that particular bottleneck.
true.
Yeah.
But the standard ones you had mentioned was, some of the Ethereum based, especially the Quorum. Are you
Right.
in some way
No,
Quorum or Besu?
No. So we just looked at the Hyperledger projects that seem to be popular, right? Or that seem to be getting a lot of traction on the mailing lists and so on. And
Besu.
So Besu and Quorum. It's not part of Hyperledger at this point, but I guess
Besu is part of
Quorum
Hyperledger.
Besu is, but Quorum is not. But Quorum and Besu have merged in some sense, right?
Yes.
Yeah. So we just picked that and Sawtooth as two other very popular Hyperledger projects, and we'd certainly be interested in working with people who know those projects well, and we can work together to see how we can accelerate those.
I saw Dano on the call earlier. I don't know whether he's still around.
Yeah, I saw him too. I was scrolling through the participant list right now. It looks like he may have had to drop off. But yeah, I mean, absolutely, we can certainly help facilitate those sorts of discussions, in a future meetup or wherever makes sense.
Mm-hmm.
So the reason I brought this up is because we are convening a standards body in ITU.
Mm-hmm.
And part of that would also be metrics lab.
Okay.
But obviously that is not just confined to Hyperledger projects.
Mm-hmm.
That'll be any project that is going to, mostly it is focused on central bank digital currencies, and ITU is a special agency of the UN, as you know, is come up with standards for MP3, various other communication standards.
Right.
So that would be useful to bring up this, sort of angle of attack in the performance part of the architectural working group, which I'm a member of. So I'm going to just mention it to them.
Okay.
Since you have already worked in Bitcoin, which is not a Hyperledger project, there may be other ways in which we could separate out certain things specifically.
Right. Yeah. So in the past, right? So we haven't done that. Our customers did that. So they tried to accelerate, the mining process, the proof of work mining for Bitcoin and Ethereum. And so obviously you can design hardware to do ET hash or, the Bitcoin equivalents, right? And, once you start designing hardware, then you can design an ASIC. And once you have an ASIC, that's going to be a lot faster than something you can do on programmable hardware. Right, so programmable hardware is usually the first step in building an ASIC, right? So you design the hardware, verify it in programmable logic, and then you move to an ASIC so that you can be sure that your hardware is correct. And if you cannot afford to build an ASIC, right, for some reason, right, maybe the volumes are not there, maybe there's not enough profit there, then programmable hardware continues to be used for a long time without anybody moving to an ASIC. And if you can keep changing your algorithm so that the hardware needs to change, right, then it would not make sense to build an ASIC because you don't want to keep spinning a new ASIC at great cost when you can just simply spin a new programming bit stream for the programmable hardware every time. So those are different trade-offs, but so we have to investigate what happens if instead of programmable, instead of proof of work, if you move to something else, such as proof of stake, then the mining part may not be the bottleneck. It might be something else, right?
Yeah.
Right.
Coming to that, there was a gentleman who said that networks were the bottleneck.
Right.
I had seen that they published lots of different profiling studies on various types of solutions, and that would reveal different bottlenecks. So in that case, a programmable hardware would be the solution, because for the enterprise blockchains, for different use cases, the bottlenecks would be slightly different. I mean, many of them would involve off-chain access. I don't know how we can improve that using programmable hardware, but also the cryptography stuff, like as you move to different countries, they have different standards. Like Russia or China, they want different standards. So I suppose you could create programmable hardware targeted to those crypto algorithms. Right.
So one of the things we can do really is, because we provide the programmable hardware, so if somebody in China wants to buy this hardware, and assuming they can still buy it, they can program the Chinese crypto algorithms on that, right? So we wouldn't have to get involved. And if somebody in some other country which has other crypto restrictions wants to program their own algorithm, they can do that.
Well, I heard that in, for example, BSN, which is a Chinese infrastructure for blockchains, they have the same crypto algorithm inside AWS or other kinds of clouds, Ali Cloud and so on. And you mentioned that your hardware is part of some of these clouds.
Yes, it is available on some of the Chinese cloud providers as well. Yeah.
So they created this way of having multiple ones. So the other question I have is, you guys really did change the node software, did you? I mean, meaning you broke it up into little different bits or different pieces, or did you leave the software, the node stuff untouched?
Okay, so I can say a little bit about that now. Then, at some point, you can examine all the code, right? But basically, what we did was we modified the node. We added to the Hyperledger node software. So we added one module, which will send out the blocks and transactions using a slightly different protocol, which is a little more hardware friendly. Right. So
you changed gossip?
No, we didn't change things at the gossip level itself, but we changed it at the level below that. In a sense, so if you think about communication protocols at the TCP UDP layer, right?
Yes.
So if you have something like TCP, it's connection oriented, so which means it becomes a lot harder for the hardware to maintain all the state, because TCP itself has a lot of baggage that it carries, right? Well, it's evolved over so many years, so there are so many things you need to support in the hardware. So it becomes tricky to support that in hardware. And so when people try to optimize it, they try to build something on top of UDP. So an example of that would be the quick protocol that Google came up with. So they optimized that to avoid the TCP overheads. And so we've done something similar. And yeah, so we should be you should be able to see all the code when we push it out. Yeah. So we did modify that. And
Yeah.
so yeah, so what we did was we said either the order which sends out the blocks, or the lead peer in each organization which sends out blocks to other peers, can run that part of the code to send out the optimized or to use the optimized protocol to talk to the hardware blockchain machine.
Yeah. So in terms of that, those alterations do not create any new security holes or anything like that.
Well, so that's a good question. I mean, we have tried to make sure that we don't create any new security holes, but you know, you'll know for sure only when everybody examines that, and you know, you can examine the code, and
Well, more
lots of
than
different people
examining.
can look at it. Right?
Yeah, you know that code review doesn't necessarily find everything.
Right.
I will
Yeah.
flag that, sorry, not to interrupt, Vipin, I will flag that there was a new question in chat. So I don't know, Daniel, if you want to, actually 2 new questions in chat. Daniel was first, and Avinash can go second.
Okay. Yeah, so I see the question here, Daniel's question about overclocking.
Yeah, Daniel, please, if you're available, feel free to ask. Oh, please ask for me. Okay, yes, yeah, go ahead, please, if you can answer his question.
Okay, so the question I see here is, are the accelerator boards overclockable to increase performance even more? So at this point, the way we have built it, it works at one particular rate. It's not overclockable. But this is programmable hardware. So in the sense, if you're building your own accelerator, you can define how fast you want it to go, right? So you can select the clock.
Great, thank you. And then Avinash, do you want to ask your question, or we could just read it off the chat?
Yeah, hi. Thanks for taking the question. This is Avinash. Hi, Mohan. Thank you for a very interesting presentation. Hi there. So my question was, I think somebody mentioned or one of you clarified that the test environment to measure the transactions per second, you'll use 2 virtual machines per server, and you'll had it at a rate of 100 transactions per second and a block size of 100 MB per block. I was just wondering, what was the throughput with the updated Xilinx chip and without the chip?
Right. So I think we had that in one of the slides. Let me see if I can share that. Okay. Am I sharing or no? Can you see my screen?
Sorry, I was unmuting. You are not sharing.
I'm not? Okay.
Yes, now I see it.
Okay. Okay. Is that better? So does that answer the question? So that's the throughput we were seeing. So the standard peer was the endorsing. Let me rephrase. Right, the standard peer here was the validating only peer to make a direct comparison, and the blockchain machine was doing validations only as well.
Okay, yes, I do remember seeing the slide earlier. So, yeah. Okay, in the earlier situation, it was about 3,000 TPS, and then that went up by about 14.5x.
Right.
With the blockchain chip that you used. And in both these situations, it was 2 VMs per server, right? In a 16-core situation. and 100 Mbps block size.
Right.
100 MB block size. Okay. Okay. Thank you so much.
Okay.
Yeah, I would just like to add one thing. The 100 Mbp block size does not really matter here because the block timeout is 1 second. So every second, the orderer would get about 100 transactions and it would create a block. So the block size, I would say, if you want to quantify it, it would be more precise to say it was 100 transactions for the block size.
Got it. Thank you.
Any other questions? Vibin, did you have additional questions? I'm sorry, I didn't mean to interrupt you earlier, but I just saw this question.
Yeah, sure. You know, there's always questions.
Oh.
There are always questions. I mean, I don't want to go down various paths, but I think this is a very useful look at this whole situation. And, you know, because like I was saying, many people are now coming further up the stack, and that will take us into real applications in the enterprise space. And I'm sure they already have a lot of them in, you know, that IBM knows about. We don't have, you know, a real look at the actual use cases. And also, if you know that inside equity markets settlement systems, the rates are huge, and
Right.
they had DTCC along with Accenture and others had published something saying that these rates are achievable, but I didn't see any other detail of what kind of transactions they use, what, you know, I mean, why do they say it's possible, you know, those kind of things. So I think any solution in the future which needs incredible throughput will depend on hardware, at least as a part of the solution. I mean, you know, so that's great. You guys, I mean, I would love to bring you back to either the performance scale or to the, you know, in terms of other blockchains, especially in the Hyperledger area, and or into the ITU thing, which is a more broad conversation about throughput. Because when you're talking about retail, central bank digital currencies, the throughput requirements are tremendous. Right. Especially if it is directly on the blockchain. Many people are suggesting it should be a layer 2 type.
Level 2, right? Yeah.
Yeah, but layer 2 has its own issues, right? Because you need liquidity providers, and your claim is not directly on the central bank. It comes on the intermediary, which is what we are trying to get away from anyway. So you know, to suggest that L2 will solve the problems.
Well, Vipin, you bring up a good point about next steps and about where we can go with this conversation, and maybe that's how we wrap up. But I do see that Nima has one more, has his hand raised, and maybe we take one more question and then we can talk about next steps and wrapping up.
Thanks, David. So regarding the throughput, transaction throughput results that you're showing, so I assume one of them, so the standard is in a, is that also a Xilinx card? So the blockchain machine, do you refer to the board as the machine, or and let me ask it in another way. So your improvements have been mainly on the Fabric code base, and partially you have integrated that with your FPGA, right? So the question is, what is your outlook for this? So is this going to be, so let's say we have 10 organizations who want to kind of host this blockchain ecosystem. are they all gonna have to use your Xilinx? Because the way I see it is that, let's say, verification or endorsements, or all these procedures, they're a little bit parallel. So like if one node is kind of not meeting the throughput or the latency of the entire network, that's gonna be the final outcome, or am I wrong?
So it's, yeah, in the case of Fabric with block validation, my understanding is the blocks are sent out to all the nodes using gossip, and then it's up to the nodes to process them at whatever rates they can process. If they fall behind, then I don't know what happens, right? Is there any way for them to send a message to the sender saying, hold off? Yeah, I'm not sure if they can do that. So in that sense, it's fairly asynchronous. And so, if you want to run something faster for some reason, or if you want to reduce the load on your CPUs, because the CPUs are more expensive, right? So that's the other use case for this kind of hardware accelerator, because this could be cheaper, right, depending on your cost, right, than a big server with 16 cores, right? So it's quite possible that you can run this without affecting the rest of the network, and the rest of the network will not affect your speed up, right? So it is possible. But again, we have to run bigger experiments to really confirm that.
I would like to add one more point to it. As Mohan said, in general, the validation is fairly asynchronous, in the sense that if one of the peers is lagging behind, they can send pull request through the gossip protocol and still get the older blocks from other peers which were faster and were able to validate and commit the block to the ledger before this lagging peer, and then they can keep validating. The problem would happen on the endorsement side. So if, let's say, a peer is doing both endorsements and validation, and it's lagging behind in validation, it would endorse transactions using the state which is actually older compared to the rest of the network state. And all those endorsements would fail at the end of the day, and that would hurt the performance. So in terms of the validation only, that's fairly asynchronous, and any lagging peers can still pull blocks from the other peers which are faster, and just keep validating and adding them to their own ledger and the state database.
Okay, so just to summarize your answers, so essentially this product will be sold as a blockchain solution, as in everyone who wants to join this organization or join this blockchain ecosystem that is using Fabric should use Xilinx products, essentially, if they want to reach these kind of high throughput and low latency that you're promising.
Well, so as a representative of Xilinx, yeah, we'll be happy if you buy Xilinx, right? But FPGAs are available from other companies as well, and in fact, people do use other FPGAs for acceleration as well. So you're not limited to a single supplier. You're not limited to a single company for a hardware accelerated solution.
Yeah. Sorry, let me rephrase that. I wasn't really talking about Xilinx itself. Yeah. I was talking about the technology. So let's say I can't have like my peer as one organization hosted in AWS on normal kind of servers, and then have the other one on Xilinx. It would be possible, I assume, but it won't achieve the high transaction throughput and so on.
Correct. So if you want to achieve this kind of high transaction rate on your node, you can use this. I mean, there are other ways of achieving a high transaction rate, you can always use a more powerful server, for example, right? You can use multiple servers. So there are many different ways to do that. And we think this would be a very cost-effective way of doing it.
Great, thank you very much.
Yeah, appreciate the questions. And I am keeping an eye on the time. And I wanted a few minutes to talk about next steps. So thank you to Xilinx for the demo and discussion. And thank you everybody for joining. I would invite Xilinx to come back to a future meetup when they have their lab available. And in the meantime, I also dropped a link to the Performance and Scale Working Group mailing list in the chat. If people have additional questions about performance in general, please make use of that as well. And again, as I had mentioned earlier, if people are based in the Bay Area and would like to present at a future Hyperledger San Francisco meetup, please feel free to reach out to me. Let me drop my email one more time in the chat. And also, if you're based somewhere else around the world, we have meetup organizations literally in all around the world. So if you're based somewhere else and are dialing in, remotely, please also reach out to me if you'd like to get connected to your local meetup group, and I'm happy to help with that as well. And I don't know if anybody else has any final words they want to share, or anybody from Xilinx or Vipin or anybody else who spoke, or anybody from Caliber, if there's any final thoughts you want to share.
I'd just like to thank everybody for attending and all the interesting questions. Thank you. And thank you, David, for helping organize this.
Of course, happy to help. One last thing I will say, if you want to share this discussion with anybody, it will be on the Hyperledger YouTube channel within just minutes after this. So you're welcome to, it'll be public. You're welcome to share this with anybody who you think would be interested in the discussion. So please do feel free to share. Great. Well, thank you everybody for dialing in. And yeah, it sounds like there was a lot of interesting next steps and ideas that came up. So looking forward to future collaboration around this theme. So thank you, everybody.
Thank you and bye.
Thank you. Bye-bye.
Thank you.
Thanks. Bye-bye.